start? Okay, so what I want to do is just sort of outline the proof of the geometric Langlands conjecture in the de Rham setting. And so this uses some input from the theory of Kac-Moody localization at critical level. And so I don't think I'm going to say very much about how that all works during the talk. Maybe I'll say a little bit if there's time permitting. But let's say I won't say much during the talk. But I will have office hours today at 3:30 in my office upstairs, which I don't know the room number for my office, but it has my name on it, and it's a small building. But what I want to do is, I think that I have sort of the impression that, this theory was really sort of initiated by Beilinson and Drinfeld, and they explained that you can give interesting constructions of Hecke eigensheaves and a variety of things. And I want to say, and then there were several decades, a few decades, and people, I think, advertised this work in a lot of ways. And the way it actually gets used in the proof of the geometric Langlands conjecture is more idiosyncratic than that, and kind of orthogonal to, I think, a lot of the wisdom about how Kac-Moody localization might be used. And so I guess I want to sort of highlight that. So that's part of my objective here is to say, how is Kac-Moody local? Like, what do we actually get out of Kac-Moody localization? And yeah, so people will say things a lot like, you need Kac-Moody localization to study irreducible local systems, and it's kind of true. We use a little bit of information in order to study irreducible local systems, but it's kind of fairly coarse stuff. Okay, so so last time, I mean, it's essential. It's like very, very essential, but it's not just like that you construct a Hecke eigensheaf using Kac-Moody localization and then prove a bunch of stuff about it. That's not really exactly the way it goes. Okay, so last time we introduced, or maybe recap overall. So let me just be in the de Rham setting, and I won't always put the de Rham superscript, but we said that there was this spectral action of quasi-co-loxus G check on the category of D modules on bun G. And then I guess we did two things. So one was that we used this to give a functor from D modules on bun G to this indco nilp of loxus G check. And this is something which surjects onto the category of quasi-coherent sheaves. And this was this functor we called LG coarse Langlands functor. And this is some kind of internal endomorphism, internal Hom out of the Poincare sheaf. So I think of this quasi-co-Leucis G check acting on this category. And if you have a, like, let's say, monoidal category acting on some module category, you can talk about internal endomorphisms. If you have two objects here, you can form an object here, which is their endomorphisms. And so that's what I'm doing in this case. And this Poincare sheaf was, or also called Whittaker sheaf, or whatever. It was some distinguished object, which ultimately is supposed to correspond to O under this equivalence. And so then we took AG to be this Langlands functor applied to the Poincare sheaf, which you can also think of as internal endomorphisms of this Poincare sheaf.
LG course?
Either way, yeah, doesn't make a big difference. Yeah, maybe LG course is a better name for it. But if you do it, otherwise it's going to lie in the image. Like there's a left adjoint here, and it'll lie in the image. Maybe that's a better way to say it. Dennis is currently trying to call me, and so let me stop him. Okay, so this is the internal endomorphisms of this Poincare sheaf. And so this was a, we said that this was an associative algebra in quasi-co of Leucis G check, just manifestly. And last time we reduced the geometric Langlands conjecture in the de Rham setting, well, in any setting, to the statement that O of Leucis G check maps isomorphically via the unit map to this AG, the unit for the algebra structure. And then, okay, so I guess I'm going to impose some simplifying assumptions. So I'm going to add a little bit more later. But my first simplifying assumption is going to be that G is adjoint. And my second one is that the genus of the curve is greater than or equal to 2. It's the same as G check being simply connected. So my genus will be at least 2. And then last time we showed and said that this was sort of a special feature of the de Rham setting, that the global sections of this AG was actually just scalars. Okay, any questions?
Yeah. Did you ever think about generalizing the statement that geometric Langlands are the proof to the case where G is a reductive group scheme over the curve?
I haven't. It's a great question. So I haven't thought very seriously about it. Okay. Yeah.
Because kind of in arithmetic Langlands, that's sort of the situation.
Yeah, sort of. I mean, to say, in arithmetic Langlands, there are lots of interesting features that come up when you do that, and there's some confusing things that come up when you do that also that are maybe a little misleading. But you can, like, for example, like one of the things people really like to do in that context is study like anisotropic groups, right? But like here over a curve, like over an algebraically closed field, every like reductive group scheme is quasi-split. And so there's something somehow, yeah. Yeah, it's fine. It probably means that there's not so many new phenomena, actually, is more what I would anticipate. Yeah, I think it would be a great project for any person who wanted to learn this stuff.
You just have to rewrite 2,000 pages in a more general context.
Exactly, yeah.
No problem.
No, okay, so yeah, actually, in this paper, to get beyond the adjoint case, we actually had to consider sort of like twisted,
Yeah, I saw that.
yeah, versions of the thing. And so it's kind of a simplified version of the question here.
Yeah.
It's like, it's a little bit orthogonal,
Yeah.
but it's, yeah. It's not exactly simplified. It's sort of moving in a slightly different direction, but yeah. I think there is interesting stuff to think about there. Okay, so last time we showed this, and yeah, and I remarked that a posteriori this corresponds to the fact that global sections of locus with coefficients in O is just scalars, and I was saying that that's a very special feature to the de Rham setting. That, of course, can't possibly be true in the Betty world.
So do you have to prove that then?
No.
Oh, okay.
Yeah.
All right.
So it's a corollary.
But do you know how to prove it a priori?
There's a paper of Frenkel and Telemann that comes very, very close to doing this. So I think you can, yeah, get it from what's in there. Yeah. Other questions? Okay, so okay, so here's going to be my input. So I had this map. Yeah, I guess I called this eta last time. So the first is that eta restricted to the locus of reducible the closed substack of reducible local systems is an isomorphism. I'll kind of comment on each of these in a second. The second thing is that if I take this AG irreducible, which is, oops, by definition, this AG restricted to locus irreducible, this is a perfect complex. So it satisfies some finiteness conditions. And the third thing is that this AG irreducible admits a flat connection with regular singularities. Okay, so this is my input, all of which is proved by Kac-Moody localization. And from here, we'll get the geometric Langlands under one additional assumption. Okay, so what are these? What's the nature of these statements? So this first one, this is really sort of the full theory of Eisenstein series. So last time I sort of indicated why the Langlands functor should be compatible with Eisenstein series. But what I didn't discuss at all is why the Langlands functor should be compatible with constant terms. And so this is a sort of, it's a pretty subtle assertion, and we do it in these papers by by computing what both sides do on Kac-Moody localized objects and then building from there. And so, yeah, and this is, this is somehow one of the most, okay, all of these statements are sort of important, but this is some kind of serious business. It's probably the case that one can avoid using Kac-Moody localization here. So there's, I think, an ongoing project of Dennis Gatesgory, Lin Chen, and Kevin Lin to do this kind of thing without using Kac-Moody localization. That's questions, comments?
If I remember correctly from last time, in order to prove that the Langlands correspondence plays well with Eisenstein series, you proved an analogous statement for the constant terms instead that by formal junctions or something like this, it's similar. But now we're saying that it's actually subtle, so which one is it?
Oh, no. Okay, okay, let me try to answer this with a little bit of a picture. So, well, okay, it's a picture I sort of drew on the first day. So I would say this a little bit coarsely. So there's kind of these three classes of objects. And then there's these Hecke symmetries. So when I think about like the general theory, I find the following principle very, very useful. The general theory, kind of idiosyncratically, like I don't really have a conceptual explanation for this fact. It's good at basically, whenever it's good at understanding the way the Hecke symmetries interact with each of these three constructions. And in addition, it's good at kind of computing Hams between any two objects here that are distinct. So as long as the two things are not equal, there's some kind of empirical observation, which is that in those cases, you can sort of reduce the calculation that you're trying to do to something that has the following flavor, like a local calculation plus some kind of local to global construction.
So by not equal, you mean they don't both live in the same class of things?
Yeah, exactly. Yep. Okay, so what happened last time was we did this actually, let's do it for like LM. And again, that's a heuristic. I don't have like I really don't have any kind of conceptual explanation of it. But so what happened last time? So we said that there was sort of commutative diagram like this. We played some games. So what were the games we played? So basically, what is this diagram expressing? So this functor of LG, it's basically about extracting the Whittaker coefficients of a given object. And so what we're doing here is kind of computing Hams from Poincare into Eisenstein. That's a great construction to do. That's A not equals B or whatever. What I was saying about formal adjunctions last time was that you could reduce this calculation instead to computing constant terms of the Poincare sheaf. That was what the formal manipulations were. And that's the same as computing Hom from Eisenstein to Poincare. So that's fine. Now, if you try to think, OK, what sort of diagram we're talking about when we do this with constant terms, then actually you get somehow much more well, let me not, not do this. Let me be more efficient. Oops. Color chalk. So now, if you try to think about what's happening when you do this like dual diagram, well, first of all, you run into the issue that you have to take seriously that this is INDCO-NILP. Because if you take the constant sheaf here and you map it into the quasi-coherent category, you're going to get 0 because it has no non-vanishing Whittaker coefficients. And in particular, it'll be 0 if you go sort of down to quasi-co and then apply some version of constant term. But you get something non-zero when you apply this constant term, and then this is an equivalence. And so somehow, like for example, for a torus, there's no difference between INDCO-NILP and quasi-co here. So you really have to take seriously the INDCO-NILP. But also, if you just think about what this diagram's expressing, it's kind of like you take a D module on bun G. Like you take its like constant terms to get down to bun M, and then you take the Whittaker coefficients for bun M. And so that's something about the like degenerate Whittaker coefficients of a automorphic sheaf, and that doesn't fall into the regime I said before. So yeah, so that's why there's somehow a serious difference. Does that answer your question?
Yes.
This also explains kind of, for me, what the idea of the argument is here. So what we do instead is we basically say, OK, there are these objects which are Kac-Moody localized. And you're able to compute Hom from this Poincare sheaf into the Kac-Moody localized guys. So that's telling you essentially what their image is under this functor LG. And also, you're able to compute the constant terms of these Kac-Moody localized things. And so that's telling you that you can compute kind of what happens along the horizontal arrows. And then, roughly speaking, you just check that the diagram commutes on Kac-Moody localized objects explicitly, and then argue that that is sufficient in order to get the full compatibility with constant terms. There's a lot to unpack in those sentences, but that's the structure of the argument. Is it OK? Are there questions for the moment? Yeah, so I was saying full theory of Eisenstein series. So it's really like another way to say this is that if you kind of unwind what's going on, it really amounts to computing constant terms of Eisenstein series in this case. And so it's like because the place where you really have to compute this, like the commutativity of this diagram, like this constant term functor is going to annihilate everything that's cuspidal by definition. And so you really care about the commutativity of this diagram on objects that are themselves Eisenstein. And so then the only thing you can think to do is really compute constant term of Eisenstein, which is sufficient to do it, but is hard because it's A equals A. A equals B. Maybe I should say it that way.
But there is some kind of Langlands formula, or?
For constant term Eisenstein? Yes, that's what this commutativity of this diagram is ultimately telling you. Yeah.
But it's much harder to prove than at the level of functions. Or?
Yeah. So for me, it's the following phenomenon. So when you compute this constant term of Eisenstein series, there's some, like let's say in the principal case, so there's some like bun T and bun G, and there's some push-pull involving bun B. And so you end up looking at bun B times bun B over bun G. And this has a stratification by the Weil group, which is looking at the generic relative position of the two reductions. And so in the world of functions, you basically split up into the different Weil group pieces and do a certain calculation there. That makes sense here also, it works, but then you really have to worry about now the difference between a filtration and a direct sum.
That's the problem.
That's the problem. That's the nature of the problem. So and that you didn't have to worry about at the level of functions. It didn't. Yeah. Yeah, but somehow you're able to get around understanding the extension problem by just computing it on the Kac-Moody localized things, where they don't really even care about that extension problem. It's like a totally different way of approaching things. And maybe it's like, from a purist point of view, kind of like the wrong way of fixing the problem, but it gets the job done. So, yeah.
But you do understand the filtration in the end.
Okay, absolutely. The answer is yes. How much work it takes to extract that from the existing results, I want to be a little cautious around. Yeah. Good question. Other questions? Okay, so yeah, and I guess okay, so 2 roughly works as follows. So
I'm sorry, just a second.
Yeah.
You didn't say it explicitly, but I guess in one you're using induction on the rank, right?
yeah.
Okay.
Yep. Yeah. Sorry. So yeah, this one I assume all. Other questions? Okay, so yeah, I'll comment briefly on 2 and 3. So for me, the idea is for 2. Okay, let me leave 2 and 3 to office hours.
Is there some sense in which 3 implies 2?
I don't think so.
Okay.
Yeah. Yeah, 2 and,
I mean, classically, if you have a vector plan, you know.
yeah. You mean if you have a vector bundle, then you have a vector bundle?
If you have a coherent sheet with a flat connection, then it's a vector bundle.
Yeah, but if you have like a D module with regular singularities, it doesn't have to be a vector bundle.
Yeah.
So, yeah, it's this kind of thing. And like,
And perfect complex is already a bit, yeah, okay, I understand.
Yeah, I mean, this looks as irreducible as like smooth, so I'm not even, like at the level of complexes, I don't care about the difference between coherent shoes. And yeah. So the, yeah, a little bit, the nature of this is like what do you really do? So what you show is that at the level, like for 2, it's something like, it amounts to showing that this functor, if you go from like here and then to quasi-coev locus irreducible, you want to say that that preserves compact objects. And it turns out that you can just compute it on Kac-Moody localized things, and then you get a formula for the result. And the formula involves these sort of operas. And it turns out that operas are they're proper over locus irreducible. So that's kind of where the 2 comes from. And the 3 is like, in some sense you get from this whole like Kac-Moody localization theory some kind of formula for what this AG is. And you can like stare at this formula, and what you hope is that it just tells you that AG is equal to O, right? that was sort of basically the way people always wanted the argument to go. Unfortunately, it doesn't tell you this. It tells you that it's some kind of cohomology of some giant space of operas on like kind of the generic point of the curve with coefficients in its dualizing sheaf. And it turns out that because the geometry of these spaces is so weird, that kind of push forward is actually the same as the de Rham push forward. So it's basically
what was the same? What was the push forward you were actually looking at?
Yeah, the push forward was omega, like in the world of coherent sheaves. And it turns out that it's also the same as the like de Rham push forward. And so in other words, it's basically just the relative homology of the space of this giant space of operas over Loxus, well, irreducible, and in particular it admits a flat connection with regular singularities, this kind of thing. Those are the words I can say more about during office hours. Okay, so so let me take these three things as the input. But in particular, I'm never saying like, oh, well, you can just, okay. People who know the mottos around this Kac-Moody localization will see that this is all very different from from I think what you kind of might have imagined doing with that theory. Okay, so so let's proceed from here. So first is I'm going to claim that this AG irreducible is actually a vector bundle. So remember, perfect complex is essentially a complex of vector bundles, well, at least locally. And so here I'm saying it's really just like, it's a vector bundle, no cohomological shifts allowed, nothing like this. And so here's the, well, there's various ways you can do this. You can do this actually directly with this theory of operas and Kac-Moody localization, but I sort of like to do it a different way. So I need some improvements in my quality of chalk at this point. Okay. So it's enough to show that for every sigma a local system, let's say I take a local system really over the ground field, that if I pull back, and let's say this is irreducible, if I take the fiber of this AG, I want to show that this is in cohomological degree 0. Let's say I call this AG sigma. And you can do this via some geometric representation theory, which is sort of fun. Okay, so what am I going to say? So if I take d modules on bun G and I kind of tensor over this category with vect, where this is like I sigma the pullback. So let me say that by definition, this is my category of Hecke eigensheaves. And what we discussed last time was that basically because we're in this irreducible world and we can forget about Eisenstein objects because of that, this category of Hecke eigensheaves is just isomorphic to the category of modules over this algebra, where if I apply the forgetful functor here, to vector spaces, this is the same as this functor of Whittaker coefficient. And I guess I don't need the eraser yet. Hit this also. Okay. Okay, so now we'll get basically confuse things a little bit. So this functor of, okay, so if I define this Hecke sigma, by our previous discussion, Hecke sigma sort of, I should say, it factors through Sheaves Nulp. Because we said any Hecke eigensheaf for sort of an actual for an actual local system, an actual k point, really like goes through this category of D modules with nilpotent singular support. And so this functor of Whittaker coefficients is going to actually factor through here. And it turns out, so I guess at this point I'm going to use sort of repeatedly in various forms a result of Kevin Lin. So it turns out that this functor of Whittaker coefficient actually is exact on Sheaves Nulp. There's some normalizing cohomological shift to put here, but let's say I put the cohomological shift. So this is this idea that Whittaker coefficients are microstocks. So this is, I guess, due to me and Joachim. And then there's another proof due to Nadler and Taylor. And our approach, I say, uses, it's kind of a quick argument using some of this AGK RRV theory plus Kevin's thesis. And moreover, it equals the functor I would call coefficient shriek. So this is using upper stars and lower shrieks. Okay, so what does that tell you now in terms of this AG? So this is sort of the geometric.
Does this mean that there's some? Sorry. Does this mean that there's some kind of like something halfway between lower star and lower shriek for which if you change the definition of Whittaker coefficient to that, then you wouldn't have any cohomological shifts?
I definitely don't know how to say that. Yeah.
But you say it's equal. That equal is also up to cohomological shifts. Yeah?
That equals also up to cohomological.
Okay, but you don't know if there's something halfway between where everything is just naturally in degree zero.
For me, it is not easy to construct a natural transformation exactly between these two things. Yeah.
But are the shifts in even degrees?
The shifts are by even amounts, yeah. Well, I mean, again, it's one of these things. You can normalize the shifts so that they disappear. Like that doesn't. The shifts don't bother me at all. It's just that you have to like get the normalizations right once and for all. I don't know if that addresses your.
Yeah, I think I just need to understand the details. But I'm not asking you to explain the details necessarily.
okay, so like again, it's like the following sort of nature. So when you deal with this Poincare sheaf, I think I gave an official definition, which is that you do like you take this exponential sheaf on A1, you star pull it back to banan omega, and then you shriek push it forward. So you can also take the IC sheaf here. So that gives you one possible room for cohomological shift. And I think in this business, you also need an additional cohomological shift by the dimension of Bun-G. Those are the shifts. Yeah. Okay, so yeah, so you end up with this sort of picture. And so what does that tell us about this A sigma now? So, so the first thing is that this category, so I have this forgetful functor down into vector spaces, and then it has this sort of left adjoint, which is given ultimately by kind of this object, this Poincare shriek, but kind of with you force it to be a Hecke eigensheaf. That's what it kind of, I guess. Maybe I should say it a little bit more like this. But then I'm saying that this is the same as this category of Hecke eigensheaves, which you can define using this sheaves nilp. And then here's some kind of functor of Whittaker coefficient, and here's some Poincare sheaf, but you should force it to actually be a Hecke eigensheaf by this sort of tensoring up procedure. And so now this functor is T exact. And so that's telling me that there's a T structure on this category so that the forgetful functor is T exact. And so that implies that this I have a T structure on this AG sigma modules. So the forgetful functor is T exact. And so that automatically implies that this AG sigma is in degrees less than or equal to 0. Just for example, if this is exact, then the left adjoint is right exact, and then you just, so that's, you run the composition, and that has to be right exact. Then in addition, Kevin also shows that this Poincare shriek sheaf is equal to the sheaf Poincare star, again, up to some shifts. I'm not going to write it. But up to Eisenstein error. So in other words, if you work in the cuspidal world, then this shriek Poincare sheaf, again defined using upper stars and lower shrieks, is the same as the star Poincare sheaf defined using upper shrieks and lower stars. And so if you think what this is saying in this case, this is going to say that this forgetful functor actually has a right adjoint, which is given by its left adjoint. So sort of unwinding what all of this is, what I'm going to say is this coefficient star is equal to this coefficient shriek. And this has a right adjoint, which is given by this star version of the Poincare sheaf. And then this Poincare star is equal to this Poincare shriek for these irreducible sigmas. And so that tells you that, that this functor also has a right adjoint. And then by exactly the same sort of logic, it's the right adjoint to the forgetful functor now, and therefore it's left exact. And so that gives you that this AG sigma has to be in degree 0. Um, Yes.
Yeah.
Yep.
Okay.
Yeah. Yeah, that's completely consistent. So, you can use Kac-Moody. You can use a bunch of things in the literature at this stage if you wanted to deduce that it was non-zero. So for me, that's not like a big concern, but absolutely, for the way I'm presenting the discussion, it could be 0. Yeah. Oops. Okay. So now I want to start using this. So I'm going to use some kind of additional geometry of this moduli space of local systems. So first, I'm going to make one more assumption. Which is that if the genus of my curve is equal to 2, then I want G-check to has no SL2 factors. In other words, we're basically reduced in the beginning to G-check, well, to G being a simple group. That's not super hard to, well, it's an adjoint group, so it's just a product of simple groups. And then I'm just saying that I want the group to not literally be PGL2 in the special case when the genus is equal to 2. I always think that this is really funny. That the argument doesn't work in this specific case.
And then you have some other argument?
Yeah, I mean, basically in type A, all of the hard things were known already. And I mean, yeah, so there are many possible arguments you can give, but yeah.
But again, using Kac-Moody localization.
That's the way that we do it in the paper. Yeah. But you could have done it using this, basically the ideas that were present in this Frenkel, Gates-Gorey-Volonen project from many years ago. So those ideas are sufficient. I mean, what am I? I guess another way to think about what sort of problem another way to think about what we're struggling against here is the problem of showing that extracting Whittaker coefficients is fully faithful on the cuspidal category. And that was sort of known just since prehistory in the case of GLN. And so you can...
But is this related to this contractibility of the space of Opers? Oh wait, no, you're saying there's an approach without using Kac-Moody localization.
There's an approach to that problem without using Kac-Moody localization. That's just the fully faithfulness of the Whittaker model. So do more or less to Piatetsky, Shapiro, and Shalika. But you can... Frenkel, Gates-Gorey, and Volonen, part of what they did was explain how to run those kinds of arguments in the geometric setup. And then Beraldo gave a sort of more souped up modern treatment of that kind of problem that's less ad hoc and more related to these kinds of methods. And yeah. Other questions?
So in this case, the irreducible locus is not the disjoint union of point, or is it?
Correct. Exactly. So that's yeah. It's connected. Yeah.
Okay. Just I wonder, because here the high category is defined in some way as a quotient, but there it's like a subcategory. So the natural map is from D module.
You mean here?
Yes.
Yeah. Okay, but this has a revision, which is this like a star.
But then the composition from hack into D module and then back to hack is not an identity.
That is correct.
Okay.
Yeah. But I guess when I write this, it's sort of that I first did this operation. Yeah. It's not literally a quotient either. I want to be slightly careful about that. But it's just that there's these directions with the arrows. And, I mean,
It's not a Varigate quotient. Yeah. Is that what you mean?
that's not any kind of quotient.
Well, isn't it a quotient in the same sense that like R going to R mod I is a quotient on the level of draft categories? Okay.
I don't know.
Or is it?
Yeah, that's a good picture for what it looks like. Yeah, like I would picture it as sort of like there's this category of D modules on Bun-G. It's some kind of category that like lives over this moduli space of local systems, and these Hecke eigensheaves are like the fiber at the point. And so you can sort of both restrict and you can also induce in this setup. Okay, so then the inputs are the following. Well, okay, I didn't need this assumption for the first thing. Just that this space of this Loxis G check is a classical LCI, which is equivalent to classical in quasi-smooth. So this phrase classical means that O is in cohomological degree 0. And this is due, I think, to Balance and Ehrenfeld. Uses flatness of the Hitchin map plus, what did I want to say? Why plus anything? Oh, plus degeneration. No. Degeneration. It's very different from saying that the tangent complex is in 1 degree. That's not what I'm saying. Like Loxis itself, just by deformation theory, in the case of, again, a semi-simple group, Loxis irreducible is just smooth. That's what the deformation theory gives you. But yeah, but I mean, it's a funny situation actually. So this implies the corresponding Betty assertion. And I really don't know a direct argument for the Betty assertion. This argument really uses this degeneration from de Rham to Higgs in an essential way. And
excuse me, what's the claim here? So is it the claim is equivalence itself, or like you're claiming that?
Okay.
So,
yeah. Okay. So let me say this quasi-smooth is some deformation theoretic condition that's extremely easy to check, and it just falls out in this case. It's basically the fact. In this case, it amounts to the fact that if you take like de Rham cohomology on a curve, it lives in degrees 0, 1, and 2. So that's what the quasi-smoothness amounts to in this case. Very, very easy to check condition in derived algebraic geometry. And then there's this much more subtle assertion, which is related to a kind of like flatness. Like you could say it's that loxus is flat over a point as a kind of equivalent formulation. And that's the statement that it's classical, that the structure sheaf lives in cohomological degree 0. And yeah. Other questions? Yeah, I guess I'm.
And that uses this hypothesis that if G equals 2, then G check has no SL2?
No, it doesn't use this. Yeah, not used so far. Yeah.
Okay. But it does use that G is greater than or equal to 2, or?
It does use that the genus is at least 2.
Okay.
Yeah, that's right. What one kind of picture you can have is the following. Well, I guess maybe let me come back slightly to this, but what you should think is that there's sort of the cotangent space to Bun G in general, and then there's the Hitchin base in general, and this moduli of Higgs bundles is always flat over the Hitchin base, but under this assumption that the genus is at least 2, that's exactly and that the group is semi-simple. That's exactly the hypothesis for the Hitchin base to be classical. So the Hitchin base involves some kind of R gamma of like some differentials, and you want to make sure you don't see R gamma of O, and you want to make sure that omega is ample, so that the cohomology vanishes.
Okay. So there is a statement you can make for general.
Just in full generality, yeah, and then the sort of obvious fact is that the Hitchin, there's a subtle assertion which is the flatness, and then there's an obvious assertion which is that genus at least 2 and semi-simple means that the Hitchin base is classical, which is just staring at the formulas. I still have this board. The next assertion is that if I take these reducible local systems inside of loxus G check, this has codimension greater than or equal to 2. So this really uses our new hypothesis. And I'll explain the proof of this later if there's time. It's kind of fun. The third thing is that loxus irreducible is simply connected. So this gets to your question about whether this is just a whole bunch of points. It's not in particular. It's connected, and even more, it's simply connected. And let's say I mean, for example, in the Betty sense, which is why that's where the regular singularities enters in. And this also uses our hypothesis.
Always irreducible?
Loxus itself? Loxus is, no, it actually has multiple connected components. So for example, for PGL2, for example, like if you have a PGL2 bundle, the moduli space breaks up into 2 components, just like.
But beyond this?
Beyond this, then it, outside of the case of elliptic curves, then yes. So this was shown by Bailenson and Drinfeld that they computed the irreducible components, which are also the same as the connected components of loxus, and are also the same as the connected components of Bun G for a semi-simple group.
Same as the connected components of Bun G, but
In the case of semi-simple groups, yeah.
but does that match up under Langlands, or does Langlands do something funny?
But that doesn't parse, because under Langlands it's G versus G check, whereas now I'm doing this crazy thing of mapping loxis to bun G, which is not something you want to necessarily think about in the Langlands. G check and G check. Yep, that's right. Yeah. Instead, the decomposition into connected components on one side is about the action of the center on the other side. So like BZ, X on BG, and it's, yeah. Okay, so with these things in mind, the argument's pretty easy. So let me take J to be the embedding of irreducible local systems into all local systems. And let me take I to be the complement of reducible local systems. So what I'm going to do is consider AG mapping to this J lower star of AG irreducible. And then this has a kernel, just, I don't know, I would write it like this, but this is like local cohomology of AG along this closed and what we're going to do is just sort of, and this is an exact triangle, and we're just going to stare at this diagram a little bit. So the first thing is that this AG irreducible is a vector bundle with flat connection with regular singularities. And so our assumption C plus Riemann-Hilbert implies that AG irreducible is now isomorphic to O on this moduli space of irreducible local systems direct some number of times. Of course, we hope to prove that this integer n is equal to 1. And let's say this is an isomorphism as quasi-coherent sheaves. So I don't really care where the flat connection with regular singularities came from. I'm not including it in the assertion, but that's the thing I need. Questions there? Yeah, I guess maybe let me make one additional comment about the C. It was kind of for Justin, but it's sort of like the, what was it?
Yeah, I just don't know how you show this from C.
From C? Oh, okay. So if you have, if you have a vector bundle with flat connection and regular singularities, so that on any complex algebraic variety, for example, that corresponds to a representation of the fundamental group. In this case, the fundamental group I'm saying is trivial. Let's say on any smooth variety or smooth stack. In this case, the fundamental group is trivial. Therefore, this vector bundle with connection had to just be isomorphic to O direct some number of times with itself, and the connection has to be trivial. Yeah. Does that answer your question? Yeah. So C plus Riemann-Hilbert, if you like.
So this is a flat connection on AG irreducible. Is that something canonical, or it's something that you construct with Casimir delocalization?
I think that there's so there's a perspective on it due to Dario Beraldo, I guess, and this is also something which isn't necessarily. I think when he was okay, so the statement is that if you there's this derived geometric Satake isomorphism, and in a suitable sense, this Langlands functor you can prove is compatible with derived geometric Satake, and you can ask kind of like what extra structure does that tell you on this AG? Like if you interpret that statement in terms of this AG, and it turns out some combination of results due to Dario and Nick Rosenblum, and then probably you need a little bit of extra work that's not in the literature, but that all would tell you that there is a connection on this. That would give you the flat connection. So you can think of that flat connection as encoding the equivariance with respect to this derived Satake. Yeah. Yeah, and there's this funny situation where like the formulation of derived Satake actually sort of took a long time to manifest in the de Rham setting. And so Dario proved this kind of principle in the Betty setting, but now there is a definition in the de Rham setting, and so someone should do a little bit of work to really make sure that it does the things that we say it does. But yeah. Yeah, but from that point of view, it's not obvious, for example, that it has regular singularities. Yeah.
So that comes from this Oper, the cohomology of Oper.
Yeah. In fact, the proof we have of this result uses the fact that affine spaces are simply connected.
Sounds good.
Yeah, but that's not true in the de Rham world, but it might, I don't know. It might be the space of local systems is actually simply connected in the de Rham sense also. And then you don't need to worry about the regular singularities. It's like something I should maybe be more cautious before saying in a talk. But it might be false for trivial reasons, but I don't see it. Okay, other questions, comments? Okay, so that's the sort of structure of this AG irreducible. Now we see that it has this very, very simple structure. And now, okay, so now using kind of this theory of Eisenstein series, this is isomorphic to this. This local cohomology of AG is the same as the local cohomology of O. Because these two are isomorphic when you restrict to the locus of reducible local systems, let's sort of say by the Eisenstein theory. And now recall the following. So on any Cohen-Macaulay variety, say y, with I from z into y closed, if you do the local cohomology of OY, this is in cohomological degrees greater than or equal to the codimension of z. So now, for us, what's happening is the local cohomology of O of locus G check is in degrees greater than or equal to 2, and I guess that's by B, is that right? Well, by A and B. So So B gives me the codimension. A says that locus is Cohen-Macaulay. That's like the definition of Cohen-Macaulay. But I just emphasize that at this point, in some sense, you're really using like some honest commutative algebra. So this is some kind of general derived algebraic geometry stuff. But the fact that LCI implies Cohen-Macaulay, well, I mean, I would say it's outside the, I mean, I don't know, it depends how you interpret it. But for me, it's outside the world of derived algebraic geometry. It's kind of just in classical algebraic geometry. Okay, so then we're done. So what does that imply? So that implies that this map from AG into this J lower star of AG irreducible is an isomorphism on H0. I guess so. H0 of this AG is isomorphic to H0 of this J lower star of AG irreducible, or just the same. If I take H0 of global sections of AG, now this is isomorphic to H0 of global sections of this AG irreducible. This we computed was K last time. And this now is just H0 of global sections of O direct sum n many times. Well, the only way that this can, I should say, this contains a copy of K direct sum n. And so that implies that n is equal to 1, first of all. I lost my eraser. What did I do with it? I keep putting it in all these weird places. OK. So that implies that n is equal to 1. And that implies that this AG irreducible is isomorphic to O of locus irreducible. And now what we need to show is that our actual map eta from O of locus irreducible to AG irreducible, which is isomorphic sort of abstractly to O. Isomorphic as quasi-coherent sheaves, we need to show that this map is an isomorphism. And for example, you can restrict to any sigma in locus G check irreducible. And then we have a map of algebras from K to a one-dimensional algebra, this AG sigma. And so that implies it's an isomorphism. In other words, kind of clearly, once we were here, we're basically done. But just to say, you could worry about whether your initial, I mean, you should worry about whether your initial map was an isomorphism. But I'm just saying, actually, that was forced on you. Yeah. So OK, that's the way the argument goes. Any questions?
I mean, would there be a way to prove that n is equal to 1 by using information from the reducible local systems, or do you really need to compute the global sections?
I would say we did just prove it using information
okay.
from the reducible local systems.
Okay, I see.
Yeah,
Okay.
that's exactly the picture I have in mind for this. Yeah, I mean, like, like in terms of, like in terms of kind of I have the following picture in terms of sort of vague analogies with like spectral theory or something. So what are we trying to do? So we're trying to compute this AG, and I explained last time that that amounts to computing Homs from this Poincare sheaf to some Hecke functor applied to the Poincare sheaf. That's like the information that's in here. And then I'm saying the following. So there's this sort of statement that global sections of AG is equal to scalars. So this is kind of the idea that we can compute that. So maybe you think of that as an inner product between Poincare and Hecke applied to Poincare. Then I'm saying that we can. That's hard to access directly, but if you integrate over all the possible Hecke functors, that's easy to calculate. You just get sort of 1 as the result. And now integrate over all the possible Hecke functors. That's sort of integrating over this moduli space of local systems. So then I have this. I sort of take that dot product and I break it up into 2 components. One coming from the reducible local systems, which I handle using Eisenstein series, and one which is the more interesting part, which is the contribution from the irreducible local systems. And I'm saying that kind of just knowing that global integral plus what happened over reducible local systems actually exactly pins down what happened over the irreducible locus. That's the sort of vague picture I have. Yeah. In reality, you need all of this kind of extra stuff about like a connection and blah, blah, blah in order to make the argument go through. But yeah. Other questions?
So then to show that when I restrict it to one point, it's non-zero, do you use the result that you mentioned last time that somehow Hecke actions acting on Poincare sheaf generates a category?
I'm using that throughout. So I guess last time, basically, in order to say that O being the same as this AG was sufficient for geometric Langlands, that it's really essential that the Poincare sheaf essentially generates the category under the Hecke action.
Okay, my question is how to show this map is not zero, the K to...
This map?
Yes.
So I'm saying it's because it's a map of algebras.
Okay.
Yeah. Just if you have a map of associative algebras, and okay. if you have a one-dimensional associative algebra, the unit map was an isomorphism.
I see.
Yeah.
Okay. I see.
Do you plan to talk about Raskin visualization in the remaining, or no, not at all?
I am going to do office hours at 3:30 today about it.
3:30. Okay.
3:30. Yeah. So.
Someone came late.
Yeah.
A few seconds late for the train that
yeah, so what I do want to say is just, I don't know. I think that this calculation of B is sort of fun. It's very similar to the calculation for C. And so I just sort of want to explain B so that we'll maybe get a feeling for where some of the hypotheses come from. So first I want to give some kind of generalities and in some kind of part of commutative algebra. So let me say a derived scheme is quasi-smooth. First of all, derived scheme of finite type over a field. Really, lots of people know this, but if the tangent complex of S is kind of in degrees 0 and 1, and what I really mean is, well, it has Tor amplitude 0, 1. And maybe so this is tangent complex for me. Another way to say it is that so I guess I'll put almost finite type. Another way to say it is that the fibers of this tangent complex are just in degrees 0 and 1.
So you said you don't know a direct proof in the Betty setting for this fact that LS G-check is classical. But is it, so it's not just a consequence of the K-pi1 property for the curve?
For the curve?
Yeah.
No.
Because wouldn't that say that if you took the...
No, but equations could be transversed like this for the evaluation of the group.
Yeah. For example, it's not true for GM.
Mm-hmm.
Yeah. Like for the group GA, this moduli space of local systems is kind of just the cohomology of the variety with a shift. So in particular, there's a contribution in degree 1. GM kind of just looks like an exponentiated version of this. And then SL2 looks like a kind of non-abelian version of this picture. Yeah. But miraculously, it's kind of, in some sense, it's purely in degrees -1 and 0. I called it S. God, I regret that. OK, for S, quasi-smooth, there's 2 invariants I can attach. So I'm going to talk about the Kroll dimension of S. Which is just, it's like Kroll dimension as you know it. It's the largest sequence of irreducible, nested sequence of irreducible subschemes that you can find. It doesn't have anything to do with derived algebraic geometry. It's just this like coarse measure of size. And then there's also the virtual dimension of S. And this is by definition the Euler characteristic of the tangent complex.
Is S here a stack or a scheme?
It doesn't. It's not going to make a difference.
Okay, but maybe I don't know what S red and stuff means for a stack. Right.
So the Kroll dimension of a stack is like you choose a smooth cover of it.
Oh, okay.
And then it's just the difference of the dimension of the fibers and the dimension upstairs.
Okay, thanks.
Yeah. So all of the properties I'm going to say reduce immediately to the situation of varieties. So that's why I'm not.
When you say two amplitude one, it's cohomological or homological?
I would say cohomological. So, yeah.
Wait, you mean homological?
No. I mean, if you take the fibers of the tangent complex, it can be.
Complex, never mind.
Yeah. Okay, so what commutative algebra tells you is that you can think about that this S is classical if and only if the Kroll dimension of S is equal to the virtual dimension of S. So I think of it as, so that's, I mean, first of all, one, under this hypothesis that S is, okay, so if S is quasi-smooth, then that implies that you have this, this condition. So I think of this virtual dimension as something which is kind of easy to calculate for moduli spaces, for example. So like imagine your S came up as some kind of moduli space, then of course you can compute the virtual dimension. I mean, that's just, I mean, it's like, of course it's a joke. I'm sure someone's going to come and tell me that there are many examples where that's not true. But for the kinds of things that come up in this business, this number is usually very easy to calculate. On the other hand, knowing the Kroll dimension of a moduli space is like a very, very significant thing. It really tells you something about kind of like how big that moduli space just physically is. It's like about constructing actual objects and not just about the deformation theory of those objects. No?
Could you have some derived structure on the boundary of some closed subset?
No. If it's quasi-smooth, then that can't. That's what this is saying. So I mean, if like, okay, if you think about it, a local model for this quasi-smooth kind of derived algebraic variety, derived algebraic scheme, derived scheme, let's say, is that you take like an affine space mapping to an affine space by a polynomial map, and you take the fiber over 0. And I'm saying that, so being classical is essentially that map is flat near 0. I'm saying that you can check flatness of a map between smooth varieties just using the Kroll dimension of the fiber. This can be flat at that map if and only if the Kroll dimension of the fiber was the expected dimension. So this is like familiar commutative algebra, I claim. This is just kind of an intrinsic way of expressing that idea that didn't mention the coordinates themselves. So you can think of the virtual dimension as like the expected dimension. In general, you also have the estimates that the virtual dimension is going to be less than or equal to the Kroll dimension, which is less than or equal to the virtual dimension plus an error term, which is the maximum over all points in S of the dimension of this H1 of TSS. And maybe just a toy local model for this. Is to take S to be 0 times 0 over this affine space. So in this case, the Kroll dimension is equal to 0. The virtual dimension is actually negative, and the dimension of the tangent of, well, say the tangent complex to S at 0 is going to equal k to the n, but living purely in cohomological degree 1. Okay, so now let's go back to our problem. So what we're doing is we're taking, well, let me switch from G to G check, or from G check to G, just for simplicity. And so now I'm taking all parabolics inside of G other than G itself. And what I want to show is that the let's say, curl dimension of this locus P is less than or equal to the curl dimension of this locus G minus 2, or let me comment that this equals the virtual dimension by this Beilinson-Drinfeld result. So again, I have this running assumption that the group is adjoint. Well, that part doesn't matter here. And that it should be semi-simple, though. And that the genus is at least 2. And eventually, we'll run into that one funny exception.
But is it so in the Beilinson-Drinfeld result, the H1 there is it 0 or not?
No, it's not. Yeah.
Okay, so that's why it's very subtle.
That's why it's subtle.
Yeah.
Yep. So I mean, for example, you can run this for the dual numbers. The dual numbers are not derived; they're classical algebraic variety. But you do have this non-trivial error term, and so, yeah. So it's kind of like, I guess what I'm saying is like, But
if you punctured your surface just once, then you would get, for kind of, so to speak, trivial reasons.
Then it's true for trivial reasons, exactly. So it's kind of, yeah, you can think of, I think it's exactly what Nietzsche was saying, was that you can think of like locus Betty as kind of G to the 2G, well, the group to the 2G many copies, but then with this single relation imposed. And so it's about the flatness of that morphism, and at least near 1. But I think it must be flat in general. But again, flatness is kind of subtle. Yeah, so what this is saying is like being classical is about this sort of equality, but in general, there's like, you can say how badly can this fail for a general quasi-smooth thing, and I'm saying there's an inequality in one direction a priori, and there's kind of, it can't, like the gap between these two things can't be too large. Like in principle, this is something very computable, and so this tells you something about how badly it can fail for a given quasi-smooth variety. Let me just give a piece of notation which is convenient for me. So I'm going to just write absolute value of H to mean the dimension of H for a group H. And why do I only write this for groups? There's no reason. It's just I think that probably Beilinson and Drinfeld did that in their book at some point, and I just stored it in my brain as convenient notation. So, okay, so in that case, what the virtual dimension is let me just emphasize, it's 2G minus 2 times the dimension of the group. That's what the deformation theory tells you. Okay, so my job is kind of to estimate this curl dimension of locus P and make sure it's not too big. So, so first, if H is reductive, then that implies, well, I guess let me give some examples. So if H is semi-simple, then let me just emphasize again, Beilinson and Drinfeld say that the dimension of this locus H in either sense is equal to the order of H, so to speak, the dimension of H times 2G minus 2. If H is equal to GM, then you can see the following. So this Loxis GM is going to map down to the moduli space of line bundles, which is smooth. It's essentially the Jacobian. Yeah, maybe I should have emphasized that being smooth is about the vanishing of this space. So in particular, this is telling you that if you're smooth, then your virtual dimension equals your curl dimension, which of course is very standard. So this is smooth, so easy to estimate. And then the fiber over the trivial bundle is, so to say, the derived scheme R gamma of omega 1. And so this is something which is isomorphic to h0 of omega 1 times kind of like the derived scheme, which is 0 times 0 over h1 of omega 1. And this is a copy of, let me just say, 0 times 0 over a1. And so this is telling me that Loxis Durham, it's essentially classical up to this one factor that it has, this 0 times 0 over a1. And so what's happening in this case is that I get that the virtual dimension is equal to the curl dimension exactly minus 1. And if you combine these two, then I get that for H reductive, which I swear will be important, the virtual dimension is equal to the curl dimension plus the dimension of the center of H. And this virtual dimension is the thing which is always 2g minus 2 times H.
K curl dimension, virtual dimension plus something.
Minus, you're saying. Yeah. Yeah, so let me just emphasize again that this is really a non-classical stack, but it's kind of only, it looks like a classical stack times this 0 times 0 over omega 1, which means its virtual dimension is too small, exactly. OK, so now what I'm going to do is take this Loxis P and map it down to Loxis M, where M is equal to P mod NP. So NP is equal to the unipotent radical of P. And this M is the Levy quotient. So that's why I was saying all this stuff about general reductive groups, is that this is some reductive group. Now let me just think for 1 second what I want to say. Yeah. OK, so now I'll make a couple claims about this situation. So the first claim is that for every sigma in this Loxis M, the curl dimension of the fiber at sigma is less than or equal to 2g minus 1, I think, times the dimension of this NP. Yeah. And so the reason for this is that this loxis, this fiber, is equal to a twisted version of loxis NP itself. And then you, if you look at the tangent so this curl dimension of loxis NP, or its sigma twisted version, is going to be less than or equal to the virtual dimension plus this dimension of H1 of the tangent complex. And this is equal to the order of this group times 2g minus 2 plus some H2 Duram, well, the dimension of some H2 Duram of a local system of rank equal to the dimension of NP. So in other words, I just have some like honest local system, vector bundle with connection of this rank, and I'm just computing its top cohomology on the curve. That's Poincare dual to the zeroth cohomology, and the dimension of zeroth cohomology is bounded by the rank of the local system. And so that's less than or equal to this plus this. And so that gives the argument. That gives this term. Okay. And so now the next thing is that the so that was claim 1. Claim 2 is that this loxis P mapping down to loxis M is actually generically smooth. And here the proof is the following. So for sigma in this loxis M, the obstruction to smoothness of the map at this point is again some H2 Duram, or by duality essentially H0 Duram of the Lie algebra, this NP twisted by sigma. So now you have a co-character 2-row check of G minus 2-row check of M. So row check is 2-row check is the sum of the positive co-roots for G, and then this is so taking all the co-roots for G and then subtracting the ones that come from M. This is a map from GM into the torus, but actually it factors through the connected component of the center for M. And so this gives rise to an action of loxis GM, which is connected on loxis M. And it's easy to see that you can modify sigma by some rank 1 local system in this precise sense of using this character to make the H2 vanish. So what I'm saying is, if you think about this in the case of so what I need to ensure is that this local system has no subquotients that are trivial local systems, and you can this sort of tensoring by some character is going to change all of the, it acts sort of non-trivially on all of the possible subquotients. So it always, there's a filtration on this n sub p, so that on each of the subquotients, this looks like just tensoring by that local, by the given local system raised to some positive power. That's the important thing. So you can always force any of the local systems that came up here to be non-trivial after this flowing. Like, let me say this more simply in the case of, what's happening in the case of the Borel. So this has some filtration on it indexed by the positive roots. And what I want to say is that you can just, you can modify this in a way that the alpha root space changes by tensoring by this local system raised to the height of alpha. And of course, you can force any given subquotient to become non-trivial by doing that operation. Okay, and so now what does this give us? So this gives us that the, let's put these two things together. So, so what I claim is that this tells us that the virtual dimension of this loxus P is going to be, sorry, the curl dimension of this loxus P is going to be less than or equal to the curl dimension of this loxus M plus, okay, plus what? The contribution coming from these fibers. But actually, I only have to worry about these fibers at the points where this map was not smooth. Plus the curl dimension of these fibers minus 1. And so now
sorry, where did this inequality come from?
Okay, let me. I'm slightly. I'm saying it a little bit. Okay, let me. Okay, I'm going to keep it here, but the inequality is coming from the following place, which, like, exactly, I should organize my way of saying this a little bit better. So, okay, so it's coming from the following place. Of course, the curl dimension of this loxus P is less than or equal to the curl dimension of loxus M plus the dimension of the fibers everywhere. Yeah, that's what.
Sounds completely logical.
Yeah, that's what dimension theory and algebraic geometry gives you. Okay, so now what do the dimensions of the fibers possibly look like? So, okay, there's this like locus where the morphism is smooth. And in this case, I know what the dimension of the fibers is. The dimension of the fibers is at most 2g minus 2 times the order of this np.
Right?
So,
I mean, you know that.
sorry, I said 2g minus 2 out loud, and I pointed to 2g minus 1. So better over this this open where it's smooth. Curl dimension of the fibers is less than or equal to 2g minus 2 times the order of this np, which is less than or equal to 2g minus 1 np minus 1. and then I have this maybe codimension 1 bad locus. And here I use the estimate 2g minus 1 times the order of this group. But because I'm over a codimension 1 locus, that's telling me that the dimension here is less than or equal to the estimate I set here.
By the way, this LSM has potentially several components.
Yeah. But when I was doing this, it does have potentially several components. But when
It works in every component.
it works because, yeah, what I was saying is this space is connected.
Okay.
I think I said that out loud. So it really does keep me within a given component when I do this construction.
Sorry, you're claiming whether the equality with the two-dimensional fibers replaced by 2g minus 1 times.
Okay, so yeah, so let me just turn this into like algebra for a second, and then say, yeah. So this is my claim, and the point is sort of like what, well, it's almost I would say into algebra. So the point is that what claim 1 alone gives you is an estimate without this minus 1, but this claim 2 got me down to minus 1.
Because of the codimension.
Yeah, I mean, because the map's generically smooth, so I can do an estimate away from codimension 1 that's a little bit better, and then I only really need to apply that claim 1 in its coarsest form over that codimension 1 locus. Okay, so now this is, we said 2g minus 2 times the dimension of this group M plus a term which is the dimension of the center of M plus this term. And let's simplify it, well, better. Without loss of generality, P is a maximal parabolic. Which implies that the dimension of the center of M is equal to 1. Well, it's equivalent. No, it's over here. Let's keep going. Okay, so now what I want to show is that this expression over here is less than or equal to the dimension of locus g minus 2, which is 2g minus 2 times the order of the group G, or dimension of the group G, which is 2g minus 2 times the dimension of M plus 2g minus 2 times 2 copies of the dimension of this NP, minus 2. Okay, so so the inequality we want. What was that? Okay, great. Yeah. So now it's algebra, which, oh God, it's so much harder to do at the board than in real life. Give me 1 second. When I move the terms around, so what I'm looking for is both like harder to do, and yeah, I want this to be less than or equal to. Wait, I'm off by. Sorry, this was 2g minus 1. Okay, so this was a 1. This is a minus 1. So these two terms cancel. Now I'm going to cancel this term from the corresponding term over here. And then I have, I'm going to take this 2 from over here on the right-hand side. And this is going to be less than or equal to, and there's a 4g minus 4 coming from this term, minus 2g minus 1 times the dimension of this np. And so this is 2g minus 3 times the order of this group np. And so this group has dimension greater than or equal to 1. And 2g minus 3 is greater than or equal to 2, well, if and only if the genus is not 2. Well, for genus greater than or equal to 2. But if the order of this np is equal to 1, that can only happen if G has an SL2 factor. Yeah, basically, this is a maximal parabolic. It corresponds to some node in the Dynkin diagram. So that gives you sort of one vector inside of this NP. But if you take any neighboring vector inside of the Dynkin diagram, then the sum will give you another vector inside of this NP, which is distinct. And you need, so as soon as you have a neighboring vector in the Dynkin diagram, then you see that this has to be at least 2. OK, so that gave the estimate on the dimension. And let me just make a remark about C from before, the simply connectedness. So there the input is the following. So there's this notion of stable bundles inside of bun G. And this has codimension 2 outside the case of interest, outside the SL2 genus equals 2 case. And you prove that estimate using exactly the same sorts of arguments that I said before. So you just you think what a stable bundle is. It's like you don't admit reductions to parabolics of a certain type. You just compute the dimensions of all of those moduli spaces, do a pretty similar, so it's a much simpler manipulation because you don't have to worry about this derived algebraic geometry stuff. You can just compute the dimensions of the moduli space and directly. And you get a similar manipulation that tells you that this has codimension at least 2 outside of that one case. And then the point is that log_sys G times, so if you take all the G bundles, all the G local systems whose underlying bundle is stable, first of all, this is contained inside of log_sys irreducible. It's going to map down to bun G stable. And this is a fibration with ANs as fibers. So the point is any stable bundle really does admit a connection. So log_sys mapping to bun G, the fibers are affine spaces, but they're potentially a little bit, they might be empty. So they're always sort of torsors for one forms, but they're like pseudo-torsors. They might be empty sets. So this map gives an isomorphism on the fundamental groups. The embedding of bun G stable into bun G gives an isomorphism on fundamental groups because of this codimension 2 thing. And it's known that bun G is simply connected for G simply connected. And so that tells you that log_sys irreducible is now some smooth Deligne-Mumford stack. It has this open, which is dense and simply connected. And therefore, it is itself simply connected. It is some standard algebraic geometry. The fundamental group of a dense open for a smooth variety or normal variety is always surjects onto the fundamental group of the variety itself. So that's sufficient for C. So again, it's just to say it's a similar sort of manipulation. So anyway, that's the argument. So yeah, thanks for.
Stuff doesn't...
It's still in Mumford, so it's like.
Oh, it's still in Mumford. Oh, you're.
The irreducible local systems and in this case there's finite automorphism groups. Yeah. So yeah. Yeah, nothing to worry about there. Okay, yeah, thanks for indulging me in, in that. So yeah, okay, see you guys next time. We'll start talking about the arithmetic story and applications to automorphic functions next time. So, all right, thanks.